Hey, good morning, everybody. This is Robert Brent. I've been associated with stressor analysis for about 20 years now. Some of you guys have probably been involved with stressor analysis for longer than that, so I'm sure that we can learn from each other in that respect. The first topic here is called ecological underpinnings. Let's jump right in. Well, I'm going to kind of liken the benthic stressor analysis process to a crime scene investigation. I'm sure most of you have seen CSI shows. I have kind of this love-hate relationship with CSI shows. They're kind of interesting, you know, but I'm kind of annoyed by them as well. For instance, they'll come in with a little vial. We collected blood from the scene, and then looks like a refrigerator. They open it, stick it into a machine. They're like, we're going to stick it into the gas chromatograph, ion chromatography, mass spectrometer, and then 3 seconds later, oh, we have the answer. It looks like that the victim was on this particular drug. Well, that kind of bothers me because usually they use the wrong instrument for this. And then secondly, they don't say anything about the day and a half of work that it takes to extract a sample and clean up a sample before it's used for that type of analysis. So I sit there the whole time watching CSI shows, kind of annoyed at some of the details. But that story aside, we're going to try to liken this benthic stressor analysis to a crime scene investigation, and you guys, okay, are going to be the investigator. It's your job to find out who the perpetrator is. Now, so what's the crime? If we're investigating a crime scene, what's the crime? Well, in this case, the crime is environmental degradation, and the victim, in the case of benthic stressor analysis, the victim is the benthic community. Okay, so that's where we're going to start. And let's take a look at the benthic community. Keep in mind that the benthic community is an indicator. Okay, it's an indicator. The goal is not just to restore the benthic community, but the benthic community is an indicator as to what's going on more broadly having to do with ecological health in the systems that we're dealing with. So when we talk about our goals for this process, our goals are not just to restore benthic community and restore benthic health. It's really to restore aquatic communities and to restore aquatic life uses. So with that said, benthics are just one indicator, right? And they're actually a very good indicator. Many of you guys in your presentations for TMDLs cover much of this information. Why do we use the benthic community? Well, it's taxonomically diverse, right? It's got all sorts of different organisms and they're found in one place. They don't move around a lot, so they're easy to collect. And they also integrate water quality conditions over a long time. They've got some key roles in the ecosystem, and all of those characteristics make them really good indicators. But keep in mind, they're not the only indicators. There's other biological indicators. Fish communities are an indicator. Health can be an indicator. Periphyton, aquatic vegetation, even mussels. Mussels in many places might be a better indicator than the benthic community. Invasive species, toxicity tests can be another indicator. So keep in mind as we're going through this process that we're not just concerned about benthic macroinvertebrates, but we're concerned about the ecosystem much more broadly. I think that the Chesapeake Bay program probably does, and when we're dealing with the bay issues, we probably do a better job of considering this than we do in our rivers, inland rivers. Within the bay, we often talk about other indicators like crab and oyster and submerged aquatic vegetation. And we mention how all of these different indicators are giving symptoms to what the problem in the bay might be. Well, the same thing actually applies to inland rivers as well. We have all of these other potential indicators. And if you're in an area where there are mussel studies, that should be a part of how we think about and how we consider restoring the ecological health of that stream. So what does that mean for us? We've got to be able to see the forest and the trees. You've probably heard the phrase, you know, that we can't see the forest for the trees. Well, in this case, we need to see both. The trees are the benthic macroinvertebrates, okay? And that's very closely what we're dealing with in the benthic stressor analysis. But at the same time, we need to back up and be able to see the forest as well. And to keep in mind that there are other aquatic organisms within these systems, and that there are other possible indicators, and that as we're restoring benthic communities, we want to have that focus on restoring aquatic life uses, which is a little bit broader. What that means for our interactions with stakeholders is that we want to try to shy away a little bit from continually focusing on restoring the benthic community, and focus on clean, healthy rivers. I think that's a much broader term that I think stakeholders can get their hands around much more easily. And it also is broad enough to include maybe all of these other efforts and initiatives that stakeholders within the watershed may have. And I would encourage you to seek out what those other initiatives within these TMDL watersheds are. If they have particular initiatives on restoring mussel populations, integrate that into what we're doing in the TMDL. And the reason for that is it will help with stakeholder input, it will help with stakeholder engagement and involvement, and it keeps us focused on the forest and not just the trees. Also, if there's other indicators that are available, use that information. All right, so let's talk about how we're going to use these benthic indicators, right? Again, just one of many indicators. How are we going to use them to determine what the source of stressors are? All right, well, let's begin back a little while ago in 1840. Justus von Liebig was a German chemist and agronomist, and he came up with the idea that's now commonly referred to as Liebig's law of the minimum. Okay, so what does this mean? Well, he was looking primarily at plants and plant growth and how can we maximize crop yields. And he found that there's a lot of different growth factors. And he was looking particularly in terms of different nutrients. There's a lot of different things that a crop needs. And he determined that, you know what, it really doesn't matter how much of all those different things there are if one of them is lacking. So if you think of the figure on the right is a barrel with wooden staves. And so this concept is likened to this idea of a barrel, and the amount of water that you can put in this barrel is equal to the amount of yield that you can get from a crop. Okay, well, what's going to determine the level of water in that barrel? Well, it's going to be the height of the lowest stave, right? Water's going to begin to spill out wherever the height of that lowest stave is. And it doesn't matter how tall all the rest of the other staves are. It only depends on the height of that minimum stave. And so how do we apply that to agricultural crops? Well, Liebig's law of the minimum says that if you're going to increase the yield, you have to focus on that one limiting nutrient, that one limiting factor. And if you raise that stave, then you can increase the overall yield of the crop. Well, in the early 1900s, Shelford, who was an American zoologist, he kind of expanded on this idea a little bit. And rather than just considering plants and plant growth, he considered primarily terrestrial organisms and animals. He also considered not just minimum factors, but also maximum requirements. And he kind of came up with the idea of the law of tolerances. This can be depicted on the figure to the right here. So we see kind of a normal distribution, okay? And on the x-axis, this could be any parameter. Now, there's two examples below that. One is pH, one is temperature. Let's look at pH, for example, okay? And then the y-axis here is the number of organisms of a particular species that are going to be in that location. Now, with this normal distribution, you're going to have more organisms if you're in the middle of this range here, meaning if pH conditions are just right for this organism. And each organism has minimum and maximum tolerances for each parameter, in this case for pH. We know that as pHs decrease and get lower, we get down to pHs 5 and 4. Within that range, we're going to lose some species, and the number of organisms is going to begin to decrease. If our pHs get too high, up in the range of 9 to 10, we're going to begin to lose species there as well, and lose organisms. And so the number of organisms is represented by this bell curve, but it has upper and lower tolerances. Organisms can't survive outside of those ranges. Well, to take this one step farther, G. Evelyn Hutchinson, who was an ecologist in the 50s and 60s, kind of expanded again upon this idea and came up with the idea of a fundamental niche. He defined this niche as an in-dimensional hypervolume of environmental conditions that allows an organism to survive and reproduce. That's kind of a mouthful. That's a good term that's useful at parties if you want to impress people. Just throw out the term in-dimensional hypervolume, and they'll think that you know a whole lot about ecology. But what does that really mean? Well, if you take Shelford's bell curve, okay, and then you add to that, that's for one parameter, but then you consider other parameters, well, then you can get a volume, as we see in the figure on the bottom left. Okay, this is considering two different parameters, each of them having their own maximum and minimum tolerance ranges for that organism. But we have more than just two parameters, right? If we add in a third parameter and a fourth and a fifth and a sixth, that's where the in-dimensional hypervolume comes from. So the N is the number of different parameters that the organism is dealing with within their environment. And so for each of those, we define an axis, and we have a minimum and a maximum range on that axis. And then we overlay that with all of the other parameters on each of their own axes, which defines this in-dimensional hypervolume, right? It's a volume in more than just 3 dimensions, which are really hard for us to picture and conceptualize. What is a 7-dimensional volume? I don't know, I can't picture that. So what I'd like you to do, and Rob sent out an email just this morning saying, if you have some materials with you in your home, you might want to grab those. I've got some transparency sheets here. I was going to give them to you if we were in person. Obviously, I can't do that. So I thought, well, what do we have around the house that could substitute for a transparency? And I thought, aha, a Ziploc bag. So if you have some Ziploc bags, grab those and a Sharpie marker and walk through this exercise with me. I think it'll hopefully help explain what this in-dimensional hypervolume is, and how small changes in environmental conditions can begin to lead to stress and can begin to lead to a change in aquatic communities. All right, so if you grab your Ziploc bag and your Sharpie, on 2 different Ziplocs, just draw 2 different bell-shaped curves. They can be any size. They can be very narrow tolerance ranges. They can be broad, and put some parameter names on them. You can pick anything. I chose temperature and hardness. So let's see if this works. I'm going to show you 2 that I chose here. All right, I've got kind of a skinny one and one that's a little fatter. And then with each, place a dot inside the curve, okay? And this dot is going to represent where the environmental condition is, okay? I also put in there color in the outside area. You can wait to do that if you want. Originally, I was planning on having different color pins for you. If you have that, it might work well. But if not, just hold off on coloring the area outside of the curves. But do put a dot on each, okay? You can put the dot anywhere inside the bell-shaped curve. I'll give you a minute to do that. Now the next thing I'd like for you to do is overlay those two transparencies at right angles from one another, okay? And then align the dots so that the dots are in the same spot. It won't be exactly the same because all of us drew different parameters and we drew different shapes of those curves. All right, so hopefully you've been able to do that and you've overlaid them at right angles. All right, it looks kind of like a mess, doesn't it? But this is where you might want to shade in the regions outside of where those two curves overlap. And the areas where those two curves overlapped are defined by this white space, this area in the middle. And here's the environmental condition. Okay, now what does this mean? Well, at least for two parameters, this would define the niche of an organism, okay? As this environmental condition in the y-axis, if it were to increase at some point, so this is the environmental condition currently, if this parameter were to increase, boom, it would be outside of its niche very shortly. If this parameter on the x-axis were to increase, that would move the environmental condition in this direction. Well, it would have a little bit of ways to go, but then at some point it would be outside of its niche as well, which means it would then limit that particular organism's abundance. All right, so a couple other steps here. All right, now if you have another transparency or two or Ziploc bag or two, you can do the same thing. Add at least a third transparency, okay, and draw one more curve. Again, make it a different shape, a different size, but put a dot on it that represents where that particular environmental condition is. Okay, and now if you take that third, and this is where things begin to become difficult for us in envisioning more than 3 dimensions, place it at some different angle. Okay, now this isn't exactly what 3 or 4 dimensions looks like, but if you place it at a different angle, what you'll begin to see is now we've got another dimension that we're trying to balance. And so here's what I've got. Yours may look similar or may look a little different. And now as it overlaps, here's the same environmental condition, but now we've kind of reduced down to this small area. All right, so we've kind of reduced again the size of this available niche. And so with each parameter, what you can see is we've got more and more conditions that the organism has to try to manage, right? And as you can think about this, what happens, and we can actually do this, if we begin to move this environmental condition, as we do that, we see that we get outside of its niche. Sometimes in short order, sometimes it might take a little more of an increase or decrease in one parameter. But hopefully this will give you some ideas what we mean by an n-dimensional hypervolume. So what does this all mean? Well, each species has a unique and complex set of environmental conditions with which it can operate within. Okay, we call that its niche. Okay, and if any of those environmental conditions begin to move in one direction or another, then we begin to bump up against some of these tolerance ranges. Okay, and as we get closer and closer to the ultimate tolerance range, we begin to develop stress. Okay, so what's a stressor? Well, a stressor is any parameter that for a particular organism is beginning to bump up against one of those tolerance ranges. okay? And the closer it gets to that tolerance range, the more of a stressor it is. Well, if that wasn't complex enough, thinking about InDimensional hypervolumes, we also have to consider that that's just for one species. But in the environment, we've got multiple species, right? We've got lots of different species, and each of those species has a different tolerance ranges. Oftentimes, you guys are very familiar with talking about sensitive species and tolerant species. What does that mean in this context? Well, a sensitive species is one with a very narrow tolerance range. Tolerant species have a much broader tolerance range, which means the environmental condition can move quite a bit more for tolerant species before they reach stress. But for a sensitive species, very narrow tolerance ranges, a small change in an environmental parameter can mean that it bumps up against this tolerance range and begins to experience stress. So if we look at communities now with multiple different species, we notice that as we begin to move environmental conditions, we may completely lose this sensitive species, but we may still keep this tolerant species. And in addition to having lots of different species, each of them with their own unique niche requirements, we also have in different environmental parameters. Might be in the hundreds, right? And there may be multiple interacting stressors. We might have more than one stressor in a particular area, and many of you have experienced this. You do a stressor analysis and you come up with more than one answer, right? And then lastly, those environmental conditions aren't just a dot. They change with time and they change with place. So all of these things we really need to consider in a stressor analysis, which means how do we consider all the different species and their individual niches? Well, that means that we need to look at community level impacts, which is why we use benthic macroinvertebrates as an indicator to start with. What do we do with all the number of different parameters? Well, we need to investigate each one. We need to investigate it individually, but we also need to realize and recognize how different parameters may interact with one another. And then lastly, how do we deal with changes in time and place? Well, that means that we need to investigate those parameters over time and space, which means more samples collected at more places, more times. All right, so let's say that for an organism, we're beginning to bump up against one of these tolerance ranges. What happens at that point? Well, there's a number of different responses, and those responses kind of increase from least severe to most severe. And those are shown at the bottom here, along with the arrow above it that kind of indicate from the left-hand side, these are least severe responses, and then to the right-hand side, most severe responses. So first, we may just see some physiological response of an organism. If pH gets too low, that organism may begin respiring more quickly. There may be some stress hormones that are developed within the organism, and sometimes these can be used as biomarkers. I haven't seen this much in benthic stressor analysis, but in research projects, oftentimes you can look at biomarkers in organisms like stress hormones to see, are they experiencing stress? And sometimes those hormones, those stress hormones, can actually indicate what type of stress it might be. Beyond that physiological response, we then may see a behavioral response. That behavioral response might be the organism avoids the area. Maybe they pack up and leave. Okay, so for some organisms, that's a lot easier than for others. Fish, they can swim away. For benthic macroinvertebrates, often what happens is they drift. And there are research studies that look at drift of macroinvertebrates as an indicator of stress. Now, what does that mean? What is drift? Well, those benthic macroinvertebrates are living down in the substrate. If conditions aren't right for them, they might just let go and let the current carry them downstream until they find another place that might be more suitable. And so if you see a large amount of drift, that's an indicator, it's a behavioral response of stress. Getting more severe than that, we move up to sublethal responses. Okay, these are things like maybe growth is reduced. or maybe the organisms can't reproduce with as much efficiency as they otherwise could. Okay, how do we tell about these responses? Well, toxicity tests are a good measure of these type of sublethal responses. Chronic toxicity tests look at growth, they look at reproduction. These are things that will happen to an organism before the ultimate response of stress, which is death. Okay, and so at the far right, we've got the lethal response. The organism can't handle it anymore, it's beyond its tolerance level, and that organism dies. Okay, for community measure, that might be indicated by we don't find that organism here within the community. But keep in mind that just because we don't find that organism in the community, it could be either behavioral response, maybe they're avoiding it. Okay, maybe they packed up and drifted away. Maybe it's a sublethal response. Maybe they're just being outcompeted by others because they have reduced fitness. They're not growing and they're not reproducing as strongly, and other organisms are outcompeting them. That's a sublethal response. Or it could be that they're not there in that present environment because they've died. And sometimes in some of these TMDL watersheds, we'll see that community conditions change very quickly over time. We go for one benthic monitoring event and we see a few sensitive species. We go back another time, they're not there. We go back another time, maybe they are there. So that could be an indication that maybe you have some of these behavioral responses or maybe some of these sublethal responses that are changing quickly over time. Another thing to keep in mind is that the community composition will likely begin to start to change long before we reach water quality thresholds. Okay, how are these water quality thresholds developed? Well, the water quality thresholds were usually developed from single species toxicity tests. Okay, so they're looking at individual species tolerance ranges. And then we do a lot of toxicity tests on different species. And unfortunately, most of our test species are those that aren't really that sensitive because we need them in order to live in a laboratory to do toxicity testing with. So oftentimes our testing, which is used to develop water quality standards, don't completely support all species. So what that means in the environment is we're going to begin to see some loss of some sensitive species. Maybe they're more sensitive than those that were used to develop the water quality standards. They're going to begin to be lost. Okay, and so that also means that when we see VSCI scores in the 50s, just below the 60 threshold, we're probably going to expect minimal deviations in those water quality parameters. Okay, we may not actually see any dissolved oxygen that drops below 5 or 4 milligrams per liter, but still dissolved oxygen could be a stressor in that particular situation. I know that makes some water quality assessors a little nervous, right? Because you're saying, wait a minute, our water quality standards aren't protective of all streams in all cases. Yeah, they probably aren't if we're looking at community level indicators. All right, so what types of responses can we have if we have multiple stressors? Well, there's kind of 3 different generic responses. And these are kind of, consider them theoretical responses because the truth might be somewhere in between the 3 of these. But there's 3 different classes of responses to multiple stressors. The first is additive effects. And that's where, think of it as 2 + 2 = 4. Okay, the effect of one stressor is added to the effect of another stressor, and that makes the problem worse. Nutrients and sediment kind of operate in this way. Okay, if you've got a nutrient issue, and then on top of it you have a sediment issue, your conditions are probably going to be worse than if you just had one or the other. Okay, but then there's another class of interactions called synergistic effects, and this is where multiple stressors have an impact that's greater than their individual effects. Think of this as 2 + 2 = 5. Okay, a dissolved oxygen and temperature kind of operate in this way, right? Because as dissolved oxygen as temperature goes down, that actually makes dissolved oxygen conditions even worse. Okay, so those two might be synergistic. And then lastly, there's another class of interactions called antagonistic effects. And this is where you have multiple stressors, and the additive effects are actually less than the sum of the individual effects. Think of this as 2 + 2 = 3. An example of this is metals and hardness. If you've got metal toxicity, but you also have a lot of hardness, that's going to reduce the toxicity of those metals. And so in that case, two different competing metals, right, including calcium and magnesium, can be competing with one another, and their individual effects are reduced because of the presence of the other. So which is happening in stream? Well, maybe a little bit of mix of all three of these. Typically, we assume additive effects unless there's some specific information that to us suggests otherwise. And perhaps maybe it's some of these examples that you see here. So this also means having multiple stressors means that we're not going to end up restoring ecological conditions until we first remove the strongest stressor. Kind of back to Liebig's law of the minimum, right? What's the limiting factor here? What's the most important stressor in this situation? That one we need to address first. But it also means that once we address that one stressor, we may not see full restoration of the ecosystem because there's multiple stressors. So while we may see some improvements if we first address the most severe stressor, those improvements may have limits. Okay, we may improve from a VSCI score of 30, maybe up to a 50. But maybe we haven't fully restored that particular ecosystem because there's another stressor involved. This also means that in some cases, we've got some kind of historic issues or some that are difficult to deal with and a TMDL really can't address, like historical land use practices, urbanization, the presence of dams. Those things may present a stress on benthic communities. And we may have other stressors and we may deal with those other stressors, like maybe sediment and dissolved oxygen. But without addressing these particular stressors, we may not receive full restoration of the ecosystem. So there's just another thing to keep in mind as we're about this process. Now there's a positive to having multiple stressors as well. And that's because most of our tools that we have to implement TMDLs, they actually work on multiple stressors as well. Things like improving riparian habitat and riparian buffers. Those improve habitat, they reduce sediment, they reduce nutrients, they decrease temperature, they filter toxics. So a lot of our tools that we have in TMDL implementation actually do deal with multiple stressors. So that's a positive on the good side. The negative side is, well, we've got multiple stressors to deal with, and we may not return to full restoration of the ecosystem until we deal with all of them. On the positive side, we have some tools that deal with multiple. All right, now here's one of those times for us to break. If you have some questions, put those in the question box. We can deal with them there. Some things that you can think about. What are ongoing initiatives and stakeholder groups within your TMDL watersheds? How can you develop some win-win scenarios with those ongoing initiatives? And then lastly, is this description of ecological stress, has it changed your view at all of what it means to conduct a stressor analysis? So some things to particularly think about, maybe jot down some notes with those things. If you have questions, go ahead and put those in the questions box. And also, if this raised any discussion issues that you think we need to discuss at a later time, feel free to either jot those in the questions box, or we can deal with them in the survey. So I'm going to pause here. I'm going to ask Rob and Katie, who are both kind of managing the question box, to see if we have any questions there we can address.
There's a good question I see in the chat box. It cites from Nesha saying, do streams with BASCI scores in the 50s present more of a challenge to address when multiple stressors are at play?
I think that they present more of a challenge, primarily because it's harder to distinguish what the stressors are, because those stressors are mild. And they're really, at that point, probably just operating on some of the more sensitive species. For that reason, you don't have a smoking gun, right? Going back to our analogy of the crime scene investigation, there's no smoking gun, right? We've got a lot of suspects and they all have motive. So we've got to really do our due diligence in the stressor analysis to investigate each stressor and to look and begin to compile what is the evidence for each of those stressors and which one has the strongest evidence. But yes, I would agree that those in the 50s probably makes your job of benthic stressor analysis a little more difficult.
How should large seasonal VASCI score differences be addressed when thinking about ecological stress response? Are there certain stressors that are more likely to cause large seasonal swings?
Yes, I think those large seasonal swings are sometimes a clue, right? Again, thinking about it as a crime scene investigation, that's a piece of evidence, and that evidence can point in one direction or another. We'll talk about that a little bit as we get more into examining the benthic data, but that is one of the things that we want to look at, is what is the seasonal pattern of those VSCI scores. Is there a particular season where scores are higher, a particular season where scores are lower? Because that can indicate what the potential stressor might be. For example, when are you likely to have dissolved oxygen problems? Well, you're likely to have dissolved oxygen problems in the late summer, right? Heading into fall. So if you see that fall VSCI scores are much lower than they are in the spring, could it be dissolved oxygen? Well, that's maybe one line of evidence that would support that. If scores are lower in the spring, well, what do we know about the spring that could bring about a particular stressor that we might not see as much in the fall? Well, that could be sediments and nutrients. Spring is a time where we usually have higher flows, and we have runoff coming out of the winter time period, particularly in agricultural areas. We're beginning to fertilize crops, and vegetation hasn't really begun to take off yet. And so we have a lot of runoff of sediment and nutrients in the springtime. And so that could be a potential indicator if we've got really low spring scores versus fall scores, that maybe nutrients or sediment at least that could be a line of evidence to suggest either of those. Yeah, good question, Lucy.
Looks like we've got a handful more questions coming in. I guess everybody got over being shy. The next question is, it also seems a little disheartening that once the limiting factor is addressed, that it may not improve the overall environmental conditions. So in the stressor analysis, should always have multiple factors that need to be addressed, correct?
So as we move through, and I think we'll probably get to this on day 4, what I like to do is I like to include things that are called contributing factors. So these are things that we may not be able to address in a TMDL, but that we know is impacting the community. This might be something like a dam. The TMDL is really not going to address the dam. Maybe another example could be imperviousness in the watershed. It's an urban watershed. The TMDL is probably not going to tear up concrete, right? But it's a contributing factor. And by listing that in the benthic stressor analysis, that imperviousness within the watershed is a contributing factor, then when we get to the TMDL implementation, those efforts in implementation that reduce imperviousness are going to be ones that are going to improve the health of the stream. And so by listing them there, even though we don't do a TMDL for imperviousness or a TMDL for dam removal. Listing those things as contributing factors in the benthic stressor analysis might give us some ability in TMDL implementation to be able to address some of those issues.
Okay. Are you aware of any studies measuring drift that were used in TMDL development?
I've seen a lot of studies on drift. I'm not sure if I've seen them directly designed for TMDL development. So no, I don't think I've seen any directly from that, although we can always look in the literature and we can pull out information from those types of research studies that say, aha, at this level of copper exposure, benthic macroorganisms began to increase in drift. And that could be a potential line of evidence in our benthic stressor analysis if we have copper levels that are above that concentration.
Okay. You mentioned mussel communities might be a good indicator. What are some of the benefits or negative aspects of adding this type of indicator or developing TMDLs to implement this measure? It seems like the unknowns, the stress responses are so great here, might be the biggest why not reason. What is the biggest unknowns associated with our current approach? You mentioned multi-stressors.
Yeah, for mussels, I wasn't necessarily suggesting that we develop a TMDL based on mussel population, but if we are in a river where they historically had diverse mussel species and we don't see that now, I think that's something that's important to bring up with stakeholders, particularly if they're stakeholders that have an interest in mussels and beginning to link their interest in maybe restoring mussels in this watershed, link that interest to the TMDL interest so that it's a win-win in some senses. And I think the more we can closely link, okay, yeah, here's one indicator, the benthic macroinvertebrates, but here's another indicator, the mussel species. And if we look historically, this river used to have 32 different species of mussels, and now it has one, right? That's an indicator that might speak more to some stakeholders than saying, well, we have a VSCI score of 32.
And finally, are there ways to account for additive stress in our TMDL models?
That's a good question. I think that really we probably try to deal with them one at a time. And if we have multiple probable stressors in a watershed, we develop the TMDL for each of them. And as we begin to implement practices, hopefully those practices will address those multiple stressors. But as we continue to monitor over time, we may see that we've made more progress with one than we have with another. And so we may want to, over time, begin to target a different stressor a little bit more as we move through TMDL implementation, depending on what we see with VSCI scores and what we see with parameter monitoring.